All right, hello everyone, and welcome to my channel. This is an educational channel. We focus on doing deep dives on theories of everything that I have come across in my research that I would like to share with the public because they're so great, so unknown that I think it could benefit some people, maybe the way that it's benefited me. And today is our 445th video on the reciprocal system of theory from Dewey B. Larson. Mr. Larson proposed his two fundamental postulates about the way the universe operated in 1959, and then he elaborated his postulates through a process of deduction to arrive at a theoretical universe. Then he took his theoretical universe and compared it to the measured universe of the scientists that they had compiled in their tables. And we're taking a look at the results of one of those studies today called Basic Properties of Matter, which is on chemistry. Larson arrives at equations for many of the basic properties of matter, such as the melting point or the specific heat, the interatomic distance, things like that, and compares them with the tables that have already been compiled. We are on chapter 5 called Heat. He derives some relations for specific heat, among other things, in this chapter. It's a very difficult chapter, but you know, you can't fault Larson. Don't ever think that I'm faulting him because this is the best we got. You know, I credit him for everything that he did. He's trying to come up with a whole new language, whole new way of thinking about things, and he didn't have any resources at his disposal, and so he did a phenomenal job. But you know, it's going to take more and more people to put it into a you know, the most coherent form, so, you know, for pedagogy, you know, so that it can be taught and learned by people. But Larson puts it out there: if you are an ambitious researcher, you can extract the information. If you're not so ambitious, then you might have to wait for the, you know, Cliff Notes version. Okay, now Larson's two fundamental postulates of his reciprocal system, which he also calls the universe of motion, because the first postulate, Larson believes that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so basically the universe is made out of motion. In particular, Larson is talking about a motion that he calls scalar motion. This is a motion with a magnitude but no direction. You take a balloon, put dots on it, blow up the balloon, all the dots will be moving away from each other. But they won't be moving in any specific direction. Rather, they'll be moving in every direction. And that is a scalar motion. That's the outward motion. If you suck in the balloon, all of the dots will be moving toward each other. And that is what he calls gravitation. And so the scalar motion is the basis of all of his, the source of this universe that he, you know, that he derives. And motion is the relationship between space and time. Space and time are reciprocals of one another. Basically, motion is a fraction, with space or time as the numerator, time or space as the denominator. Just think of speed. This is our most basic kind of motion. The bike is going 12 miles per hour. 12 miles of space in 1 hour of time. That is space over time. That's a fraction. Space over time, that's speed. If you decide to double the speed, then you can say the bike is now going 24 miles per hour. Or alternatively and equivalently, you can say the bike is now going 12 miles per half hour. You can multiply the space or divide the time by 2, and that is a reciprocal relationship. So at least in speed, space and time are reciprocals of one another, and motion is a fraction with space or time as the numerator and time or space as the denominator. Larson extrapolates from that, and he applies it to all of our scientific phenomena, equating them to motions, such as matter, energy, force, acceleration, momentum, pressure, power. These are all relationships between space and time, keeping in mind that space and time have 3 dimensions, as does motion, and space or time come in discrete units only, as does motion. Now, another main thing that you have to keep in mind with the universe of motion is that you have to be able to understand that motion exists before anything that is moving. You have motion before something moving, and that motion is this progression, and it's the progression at 1 unit of space per 1 unit of time, which is also known as the speed of light. Okay, so that is what Larson calls the progression of the natural reference system. And that divides the universe in half. He calls that the neutral point or the null point. So half the universe is moving faster than the speed of light, half is moving slower. The half that's moving slower is called the material sector. The half that's moving faster is called the cosmic sector. The rules are the reverse in each sector, or the reciprocal in each sector. In the material sector, you have 3 dimensions of space in a still frame, and progressing time or scalar time, because you're anchoring to space. And so when you anchor to the space, you put it still, and you're basically abstracting. This is the way you see it. That's not reality, though. And then in the cosmic sector, you have the opposite, where you have 3 dimensions of time in a still frame, and you have clock space. Space is always progressing, getting later and later and later, or getting farther and farther and farther apart. Time is progressing in the material sector, getting later and later and later. Okay, I'm going to try to get started with this a little bit earlier today, and I'll try to explain any dangling omissions to the information that you need to understand this as we go along. Right now, he had just gotten done talking about these specific heat curves and how there are parallel specific heat curves depending on the initial level. Now, the initial level is always there. This is the progression of the natural reference system. It is omnipresent and eternal. This motion is always in the background of the universe of motion. It has to be considered in every interaction. Okay, although this initial component of the molecular motion is effective in determining the temperature, its magnitude cannot be altered, and it is therefore not transferable. The progression cannot be altered. It's always the same. And consequently, even where the initial level is negative, there is no negative specific heat. Now specific heat is the amount of heat that you have to add to something to raise a certain amount of it by a certain temperature. Okay, where the sum of the negative initial level and the thermal component is negative, the effective specific heat of the molecule is 0. It should be noted in passing that the existence of this second fixed component of the specific heat confirm the vibrational character of the basic constituent of the atomic structure, the constituent that we have identified as a photon. Okay, so in Larson's atom, we start with a photon. And a photon is, in a universe of motion, a photon is the only thing that is actually not moving, because the photon is just being carried by the progression. The progression is always moving at the speed of light. So the photon appears to be moving at the speed of light, but it is actually a vibratory motion or a wave-like motion that is kind of like basically stuck on the surface of that balloon. And so it is being carried by that balloon outward at the speed of light. But you have to, it is basically a reversal of the progression in one dimension. So the progression, again, just like motion, space, and time, is three-dimensional. Now these dimensions are independent of each other, the scalar dimensions, and so it's being the progression is reversed in one dimension, but not in the other two. So it's still being pulled at the speed of light in the other two dimensions, and it makes a wave-like motion basically on the surface of the balloon. And now there's dispute as to how that motion arises. Larson says it's from the superimposing of a vibrational motion on a translational motion. Other people say it's the result of two rotational motions that interfere with each other and create a wave. Regardless, you have to have that photon, and really eventually you need to have two photons in order to construct matter. And so the matter is constructed on the photon, and basically the photon is a vibration or a wave-like motion, and the atom is the rotation of that vibration in three dimensions. So you have to have basically two-dimensional rotations of the vibration to get to the atom. Okay, so the demonstration that there is a negative initial level of the specific heat curve is a clear indication of the validity of the theoretical identification of the basic unit in the atomic structure as a vibratory motion, because it can be positive or negative, this addition to the specific heat curve. The equation that was given above, which, let's see what that was. Oh boy, got to go pretty far back to get to that equation. Here we go. It is the change in heat per time is equal to 2T over n to the third power. N is the number of, I believe, the number of rotational factors in the atom, and T is the temperature. 2T comes from the integration of the original expression, which was T squared over N3, which is just the heat. And that comes from the fact that radiation is four-dimensional, and it is reduced to two-dimensional because when you observe an atom, you observe it in what he calls the time region, which is a subset of the material sector. And in this subset of the material sector, it's a subset because of the discrete unit postulate. There's a minimum unit of space and a minimum unit of time and a minimum unit of motion. The minimum unit of motion is 1 unit of space per 1 unit of time. The minimum unit of space is 1 unit, which is like 1/500,000th of an inch approximately, 2/millionths of an inch. And that, when you don't when you have interactions like atomic interactions and molecular interactions that are occurring in less than 1 unit of space, then you don't have space, because you have to have a full unit. If you don't have space, then you only have time, because the universe is made out of space and time. So it has to be one or the other or both. And so when the action occurs in the time region, the real thing is happening in time, but we don't see in time, we only see in space, because we're anchored to the spatial reference system. And so we perceive it in what he calls equivalent space. And equivalent space is 1 over t. S equals 1 over t. Space is the reciprocal of time. And then you have to put it over another t, because that is speed. Space over time is speed. Equivalent space, or equivalent speed, is 1 over t squared. So we see it as a second power relation. And so we have to reduce it by the second power to put it into the t squared as opposed to t to the 4th. Part of that equation. And then when you differentiate the equation to get the specific heat, then t squared becomes 2t. And that's all over n to the 3rd power. Okay. Let's see here. Okay, that's the equation 5-7. Can now be further generalized to include the specific heat contribution of the basic vibration, the initial level, which we will represent by the symbol I. The net specific heat, the value as measured, is then 2t over n to the 3rd plus I. I believe that even though he doesn't put parentheses around the 2t over n to the 3rd, the plus I is not part of the denominator there. It's separate from the 2t over n to the 3rd. Okay, where there is a choice between two possible states, as there is between the positive and negative initial levels, the probability relations determine which of the alternatives will prevail. Now, just as an aside, Larson uses probability for much of his deduction process for deducing what the universe actually looks like. The universe, that's really his second postulate. The universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute and its geometry is Euclidean. Now, the second postulate has been disputed by many of Larson's followers, especially the Euclidean geometry part, and in some sense the commutative mathematics part. But Larson, probability relations are part of the structure of this universe, and so he follows a lot the principle of plenitude. What can exist does exist, but a lot of things are excluded because they can exist, but they are generally overruled by other things that are more probable. So some things can exist but don't exist in the kind of numbers that are more than negligible. Okay, so the probability relations determine which of the alternatives will prevail. Other things being equal, the condition of least net energy, is the most probable. And since the negative initial level requires less net energy for a given temperature than the positive initial level, the thermal motion is based on the negative level at low temperatures, unless motion on this basis is inhibited by structural factors. Addition of energy in the time region, that's the inside region of the material sector where there is no space because the interactions are occurring within a unit of space, and so they occur in time. We call that the time region. There is a reciprocal region in the cosmic sector that is called the space region, and this occurs inside one unit of time. And that is the realm of cosmic atoms and cosmic molecules, which cosmic atoms are also known as antimatter or mesons. Okay, addition of energy in the time region takes place by means of a decrease in the effective time magnitude. Okay, so energy here is basically like temperature. You add energy in the time region by subtracting time. Now that makes sense to me, but we'll just go on. But that makes sense to me because the higher the energy, higher the temperature, the less time involved. This is just, your basic chemical processes. If something is at a higher temperature, it does whatever the thing is faster. And it involves eliminating successive time units from the vibration period. So if we're vibrating, this vibration takes 2 units of time. Well, to speed it up, now you say, well, this vibration just takes 1 unit of time. You've doubled the speed, doubled the energy. Or, yeah, I guess, maybe quadrupled it. The process is therefore discontinuous, but the number of effective time units under ordinary conditions is so large that the relative effect of the elimination of 1 unit is extremely small. And then, so I would also say that as I said, the natural unit of space is about 2/millionths of an inch. The actual unit of time is 1.52 times 10 to the minus 16 seconds. So it's less than 1/6 quadrillionth of a second. So when you cut off 1 unit of time, you're not really making too much of a difference here. So, but the number of effective time units under ordinary conditions is so large that the relative effect of the elimination of 1 unit is extremely small. Furthermore, observations of heat phenomena of the solid state do not deal with single molecules, but with aggregates of many molecules. And the measurements are averages. For all practical purposes, therefore, we may consider that the specific heat of a solid increases in continuous relation to the temperature, following the pattern defined by that equation that we just looked at. As pointed out earlier in this chapter, the thermal motion cannot cross the time region boundary until its magnitude is sufficient to overcome the progression of the natural reference system. So the thermal motion cannot get out of the time region until its magnitude is sufficient to overcome the progression of the natural reference system without assistance from the gravitational motion. That is, it must attain unit magnitude. Now, the thing that you have to understand here is that in the time region, where you're crossing that unit boundary, just like where you're crossing the unit speed boundary, moving from the material sector to the cosmic sector, the rules invert and you interchange the roles of space and time. So in the material sector, you've got coordinate space, or 3 dimensions of space in a still frame, and you have clock time. The time is getting later and later and later. In the cosmic sector, you have the reverse. You have coordinate time and clock space. When you cross that unit speed boundary, the rules reverse. Well, the same is true about the time region in the material sector. When you cross that boundary, the rules reverse, and now the progression is moving inward and gravitation is moving outward. Unlike in the material sector where the progression is moving outward and gravitation is moving inward. So, in the time region, the progression is responsible for things such as compression, moving things closer together, whereas gravitation is responsible for moving things further apart. And here, in order to get out of the time region, which is what something has to do, the time region is really for the solid state. 3 dimensions, the solid state is 3 dimensions in the time region. If you go to the liquid state, then you have 1 dimension outside of the time region. The gaseous state has all 3 dimensions outside of the time region. And so the thermal motion, the temperature, or the motion that causes temperature, cannot cross the time region boundary until its magnitude is sufficient to overcome the progression of the natural reference system without assistance from the gravitational motion. That is, it must attain unit magnitude. So, the thermal motion must attain unit magnitude before it can overcome this, contracting force of the progression. And it doesn't get assistance from the gravitational motion. And I'm not exactly sure why that is. I'll try to figure that out. Again, this is all detective work for us. There's going to always be a ton of loose ends that you don't exactly figure out why certain things are. But if you just keep it in your mind, eventually he'll probably answer the question. He doesn't put it all right there for you. Because he's just trying, he's just one guy. He's just trying to do the best he could. And he did a damn fine job. Okay, the maximum thermal specific heat, the total increment above the initial level, is the value that prevails at the point where the thermal motion reaches this unit level. We can evaluate it by giving each of the terms T and N in equation 5-7, which is the 2T over N to the third unit value. On this basis, we find that it amounts to 2 natural units, or 3 times the gas constant, 3R, because the gas constant is equal to 2/3 of a natural unit of heat. Everything in the reciprocal system is in natural units. And generally, the natural units are based on the units. So with energy, the energy is time over space, because every phenomena in science is a relationship of fraction with space or time as the numerator and time or space as the denominator. So energy is time over space. So basically what you're doing for the units is you're taking 1 unit of time and dividing it by 1 unit of space. And that is the natural unit of energy. Now, there are some exceptions to that, because Larson has to kind of relate these things to values that occur naturally. So the natural unit of speed is the speed of light. And so he adjusted his natural unit of space to accommodate that. But he used the Rydberg frequency from one of the frequencies of hydrogen to determine the unit of time. And then he adjusted his unit of space to make that fraction, space over time, equal to the speed of light. Okay, here in this example, he's using the gas constant for the unit of specific heat, even though it actually only is 2/3 of a natural unit. But he's saying that we got to get to 2 natural units before we're able to get out of the time region. And so that would, I believe that would be the melting point, where you get out of the time region that's in 1 dimension. Maybe it could be the melting point, the boiling point, where you get out in 3 dimensions. We'll see. Okay, the normal initial level is -2/9, which comes from the photon. Comes from 2 photons. And the explanation on that is too long to get into, even if I understood it perfectly. And of this, 3R is specific heat, or -2/3 R. So the normal initial level of -2/9, which comes from the photons, has to be multiplied by this 3R, and then you get -2/3 R. So the 3R total that you need to get in order to get to the unit boundary, that time region boundary, is then reached at a net positive specific heat of 2 1/3 R. 3 minus 2/3. 2 1/3 R. Okay, I think we're going to stop there. This is a fascinating study, and it's very hard to follow. All you have to do is just not get discouraged and just keep hanging in there. You'll get bits and pieces of it, and I'll try to walk you through to the extent that I can. Just keep in mind that I'm a student of this and not a master of it. I just am doing the best I can too. I'm probably a little bit more advanced than you, but I am not a scientist. And I think that is actually part of Larson's problem, is because he's writing for an audience of scientists. And he should have written for an audience of lay people, because the scientists are too engrossed in their own paradigm to actually take something like this seriously, most of them. And so he really didn't get a whole lot of play from scientists, because they rejected him out of hand, which is what my experience too. When I've talked to scientists, they've just rejected it out of hand without even listening to me. Okay, thanks for tuning in today. We'll see.